Thank you very much for this invitation. It is the first time I'm speaking in the audience since the beginning of this pandemic. So I'm very emotive. No, it's okay. That's fine. I'm very pleased because it doesn't fit exactly what Habib wanted for me to speak about the source localization technique. You'll see why, because there is something that is moving in this perspective. So I will speak about what I've done during the last 3-4 years about sleep and EEG and what changed for the kids, for the children during sleep. That makes probably some maturation of the brain during sleep with respect to the cognitive assessment of the brain function for the kids. So it is a part of the study that has been done with a lot of people. Julie Carrier at the Uni of Montreal, which is the guru in sleep studies in Montreal, with also a lot of other people, times that we know here, of course. And some students, Maud Bouchard, Véronique Latreille, Lina that I will mention, of course. And there is all the data has been collected in Lyon, because I have a large cohort of kids that have studied. And it is interesting because the measurement has been done at home, not in a lab. So probably the data are quite nice with respect to the ecological way of measuring brain activity for those children. And there is also people like Michael Foti, one of my students, who is also working and collaborating with this over here. So we have to hear the audio. Out a bit closer to the microphone. I don't know where is the microphone. So I will speak to the computer. Okay, I will speak more louder. Yeah. Okay, so let's start. If I can. Okay. I'd like to start with this kind of picture because indeed it is exactly what we want to do. We want to decode. It is also true in the brain source imaging, but here in this talk, I would speak about the signals that we can measure on the head, on the scalp with the EEG. So we want to decode, and we want to decode the partition of the brain activity. It's a picture that I love because indeed is also in this picture the idea that we have to decode in terms. I have to talk to this guy.
Yes, here I can see it. You can
if I sit, I would sleep. So yes, we want to decode in terms of the time courses, but also with respect to the frequency. So of course, this picture is very nice because it illustrates exactly the strategy to decode in the time frequency domain. Even I will not speak about wavelet, and this is a pity because I love to speak about wavelet, but it will be not part of this. So anyway, what you see on the top, it is one recording about sleep, and in particular, this combination of waves, the slow waves and the spindles that I will mostly speak about during this talk. And I will not speak about that, but it is the purpose also to decode, but also to make the localization of the very particular part of the waves, of the rhythmic activity. And this is exactly the purpose of the long term or mid-term, because I'm close to the retirement. The mid-term of my research is to decode, but also decode very specific part of the rhythmic activity. And in this work that has been done a couple of years ago, we made the localization of very specific part of the slow waves, the hyperpolarization and the depolarization of the slow waves, to see how much the brain activity was localized and moving, in particular in this case, from the frontal to the more median temporal lobes during the slow waves. But again, I will not speak too much about the source localization today. I will speak mostly about sleep and what is happening during sleep for an aging. So during the aging. So under normal conditions, sleep is a recovery process, we know, and there is the most important biomarker in to the response of this spontaneous activity during sleep. We know that during the non-REM sleep, I will not speak about the REM sleep, even if it is a very interesting part of the sleep, but it is very complicated to study the REM sleep because there is a lot of artifacts. In fact, the artifact of the REM sleep are the ocular movement. It is not artifact, it's part of the biosignal that you have to use to detect the REM. So we are just starting to investigate the REM sleep, but I will speak mostly about the non-REM sleep, because during the non-REM sleep, there is no activity of the ocular movement. There is nothing in the EEG. Well, we expect that there is nothing in the EEG reflecting the ocular movement. There is other artifacts that are more standard to remove. And there is the grapho elements, the oscillatory, the rhythmic activity that are very specific to the cognition during sleep, the slow waves and the spindles. So the slow waves, it is low frequency, below 4 Hertz, and with a helocant amplitude, it is exactly the slow wave that you have seen before. And as this very first one about the all work that have been started the discipline, it was to see that under, for example, the sleep deprivation, there is a modulation of the slow wave activity, the delta band, doing across the time during sleep. First cycle, second cycle, third cycle, and we see that there is a dynamic of this rhythmic activity across the time during the sleep, and this is exactly the purpose to see more carefully or more in detail what is happening during the sleep in kids in the treatment. I will not discuss so much about the mechanism because it is well documented, of course, but only to remind that from this work of Thériault and Timofeyev in Laval University, there is those three main grapho elements during the non-REM sleep: the spindles between 7 and 15 Hertz, the delta waves, or all the slow waves between 1 and 4 Hertz, and the particular part of the slow waves between 0.5 and 1 Hertz. So this is a kind of nomenclature that we are using to describe the rhythmic activity during sleep, the particular biomarker. They are all involving this thalamocortical loop between the cortex and the more deep structure of the thalamus structure, and they are organized. They are organized in a way that there is also interaction between all those graph elements. And this is a particular point that I would like to illustrate here in this talk. So, from my point of view, I'm not an expert about sleep, honestly. I'm interested by sleep because it is a unique period of the life where your brain is working for himself. And you try to make the best for you to prepare the activity, even in the mid or the long-term activity during the active period of your life. So it is interesting because it is, from my point of view, a pure resting state. But there is a lot of mechanisms. Of course, we know that there is a lot of mechanisms of sleep, and that is the reason why there is so much people involved in sleep studies. It is because, in fact, there is a lot of things to know about the brain, the healthy brain, but also some pathology that may emerge during the life, and you may discover during the sleep a lot of signals that may predict, in fact, what is happening for the health in the human being. So this is important to have this, again, to know how to decode the brain activity with respect to this particular elements, the rhythm, but also the arrhythmic part of the brain, this is arrhythmic part of the signal, because we know that there is a lot of things to learn about the healthy brain. So if we want to detect those graph elements, we need algorithms. This is my part of the thing in which I have a lot of pleasure to make some algorithm that try to reproduce what an expert will try to do on the signal. And in particular, the detection of the slow waves. This is a classical detector. You have to filter between 0.3 and 4 Hertz. And then what is interesting in the slow waves, you have some objective thresholds. The slow waves, in most of the work, you have the peak-to-peak amplitude between the hyperpolarization and the depolarization phase of the slow waves. You have to be above 75 macrovolts. And you have also the constraint to assess that there is a slow wave, to have the hyperpolarization phase to be higher than lower because of the minus 40 microvolts. And if you meet all those criteria, also some criteria of duration, then you mark a slow wave in your registration. And this is the detector that people are using most frequently. Of course, we know also that the slow waves will change during life with aging. So the question that we wanted to know is, does those criteria of detection are the same for adults, for young people, for what happens with the aging, and with sex also, between men and women? So this is the first work that have been done a couple of years ago. And it was published, and it was the work of Lina and a lot of people around this work, to see if we could learn, as exactly in the spirit of the learning algorithm, can we learn the threshold of detection? So I will not explain exactly what was the strategy to learn the threshold, but in fact, what we discovered was that, and we test, of course, this learning. It was exactly the learning and testing strategy to see all the threshold. But the lesson was as following. This is the standard criteria on the top. And what we obtained was, if we learn exactly what is the criteria to adapt with sex and age, for the women, females, we see that the criteria have to be a little higher than what we are using in standard. And when for the old woman, there is a deficit. The criteria has to be slower because, in fact, there is an attrition where the amplitude reduces with age. And for the men, it is the same. And we see that the criteria of 75 is a bit lower for the young people. If we want to learn those criteria from the database, sort of big data strategy. And what is most important for us, it is very critical, with aging, we have a reduction of the amplitude that is drastic as compared to the world. And we see that the criteria of the detection are very sensitive with age and sex. And this standard detector may be biased, not very, could be close to what we need for the young people, but for the elderly people, it's clearly not adapted. So this is the first lesson. The detector should know about sex and age to be fair with respect to the inventory of the slow wave. So sleep slow wave change during the middle years of the life. This, in fact, this was has been done in order to respond in some sense to this work that has been published a long time ago, but it was an important work. It was among the first work to show that indeed all those graph elements, in particular the slow wave, change with aging. The question was, if we take care about the detector itself to reproduce and to be fair with age and sex, does this changement of the slow waves, the characteristic of the slow waves are indeed changing with age. So it is a sort of, if we control with age and sex, does the property of the slow waves change indeed with aging? And the answer was yes. But it was a matter of detector. About the feature of the slow waves, there is a couple of characteristics that we will use to characterize the scarf elements. There is density, how much slow waves they are producing during 1 minute of sleep. And this is this change with sex and it change with aging. So the first girl, and this is the old work in 2011. This is what's produced by the young people, and when you get older and older, you will reduce the number of slow waves that you produce in the night. And it is true for men, it is true for women. It changes with respect to the topography, change between the frontal to the occipital electrode, but there is a global reduction of the density. And this was also obtained even if the detector were adapted to sex and age. So it is a property of the slow waves. So about, again, there is some boxes in English here to help the reading. The rest of the text is not so much important. For the density, overall, the density decrease with age, with a strong reduction in onset of sleep, as you can see here. The amplitude of the slow. Yeah, that's true. I can use. Yeah, that's true. Yeah, that's it. There is also a reduction of the amplitude of the slow waves. The amplitude of the slow wave decreases with aging, but this reduction is less important at the beginning of sleep. And there is also a reduction about the slope. And the slope is important because this feature is associated with the work of Vygotsky, for example, is usually associated with the intensity of the synaptic strands engaged during this slow waves depolarization. So all those parameters decrease with aging. And again, the question is, can we see what we see with children? Because all those studies are mostly done with adults, young adults, and older adults. So I will know that there is this kind of introduction. I will try to make some question, some hypotheses. There is a trait-like characteristic of sleep EEG across adolescent development. So this is more focused on the adolescent and the young people. And the third question is, post-spectral analysis, I am fond of spectral analysis. I will see why the spectral analysis can be revisited today. It will be a part of the end of this talk. So the spectral analysis accounts for overnight sleep in children. So again, what is how much the spectrum is changing during the night for the kids? Second question about the characteristics of the sleep slow wave in children and adolescents. So there is this work that has been published a couple of years ago, 12 years ago. And from this work, what we can keep in mind, there is a change in the slope of the slow wave. Again, the slope, it is a slope, it is a ratio of the amplitude peak to peak of the slow waves with respect to the duration between the depolarization and the hyperpolarization, depolarization time. So this slope change is with age, as you can see, between the children and the adolescent. And what is interesting, it changed also with respect to the non-REM period across the night. So there is a process that changed in time about this shape of the slow wave. And this is something that we would like to assess with kids, children, and to see how much during the night, in a very detailed, or at least with some more detailed description in time, how much it changed with respect to the other criteria. So the question here, how does the slow wave slope change during the child sleep, the sleep of the kids? Do we have, and this is important for us, do we have another slow wave biomarker that would evolve in the same direction? And you will see that maybe there is another thing that we could characterize during the slow waves that may be more accurate than this particular biomarker of the slope. Question 3 about the spindle maturation. So the two questions was about the slow waves, and now we are looking at the spindle. The spindle is more around 13 hertz. The duration is more between 0.5 to maybe 2, even 3 seconds. And it is more related to the cognition, the thalamocortical loop of this process.
What is spindle?
Pardon?
What is spindle?
The spindle, I will show you a spindle in a few minutes. Spindle is an oscillatory pattern that is around 13 hertz. And it is a thalamocortical loop involved producing this very short duration activity that you reproduce again and again. And it is believed that it is related to the memory consolidation during sleep. Okay. So here, this oscillatory pattern, this spindle, with age, we see that the frequency is between 11 to 13, so around 13. So this is below 13, and this is not interesting because you and I were making spindle more faster spindle, the frequency increase with aging. But still, with age, we see that the frequency will change across age in a linear slope. And also the density, the number of spindles that you are producing per minute will change across the aging. So there's the maturation, and people believe that this evolution reproduces the maturation of this brain activity during sleep because there is connection involved with respect to this oscillatory pattern. So the question is, does this maturation manifest itself at the level of the night of the sleep in the kids? Then we see also that something's changed during the night of the kids. Finally, we spoke about the slow wave, we spoke about the spindles, and people also are speaking about the coupling between slow wave and spindles, the coupling between frequency, between the rhythm. So the question here, is there some maturation behind this coupling during the night of the children that makes this coupling more efficient at the end than it was at the beginning of the night? Okay, now this is a code that we are using. So this beautiful pizza on the right side show you how we describe the night of the kids. So the colors are related to what we call the block. A block is a number of epochs, and the epochs, the subdivision of the night, is in 6 blocks. Each blocks are of the same kind, of the same duration in non-REM. So we take the full non-REM duration of the night for the kids, and then we subdivide in 6 parts. All in these 6 parts of the same duration, you may have not exactly the same number of epochs, but at least it is for everybody to be the same subdivision of the duration of the non-REM sleep. So the fact that there is some holes is only because there is REM, of course, period that we don't know, or we may have some artifacts and some epochs will be removed from the picture. So all the kids here are sleeping with the 6 color, with the 6 blocks that you can see, and all the measurement, all the metric that we will use will be with respect to the block. The first block at the beginning of the sleep, and the very last block, the 6th block at the end of the sleep for all the kids. What else? With most of the results were similar for all the electrodes, but in fact we used C4, so central electrode. It was in fact the electrode in which we had the lower number of artifacts, so we had a lot of them. 35 children, and there is no difference between the kids, even if, and I have to say that, initially we have also some cognitive measurement about the intellectual performance of the kids. But this is another story, but here all the kids are out together. So let's speak about the slow waves. The slow waves is exactly what you can see here in this illustration. So what is the slow waves activity for the children across the night? And of course, we will describe the properties of the slow waves that we can detect in the children. And you see that you have the block 1 to the block 6. So here, 6, sorry. So this is the night that you have horizontally. And during the night, we can see the decrease here of the density. So the kids are producing a lot of slow waves at the beginning of the night, and then there is a sort of plateau. And this plateau occurs in the middle of the night. In the gray line, it is the adults, the elderly and the adult people. So they make, of course, a bit more. We know that there is a reduction, but the decrease are the same kind of tendency. In the middle, it is the amplitude peak to peak. And remember that this amplitude peak to peak tends to reproduce the amount of the neural mass involved in this process at some point. So there is a huge amplitude at the beginning of the night, and then there is a decrease, the slow change about the decrease in the middle of the night for the children. And finally, on the right-hand side, it is the dynamic of the slopes. The slopes, it is the ratio between, again, the amplitude to peak to the time that it takes to make this phase transition between the hyperpolarization and the depolarization. And again, it is high at the beginning of the night, and then it decreases, and there is a sort of plateau, the same kind of behavior that you have for the amplitude, but not exactly the same. So this is the property of the slow waves for the kids. Now, what we have done during this famous pandemic also was to ask ourselves if there is other biomarker of the slow waves in the slow waves that could be of interest. And for some reason that is long to explain, suddenly we were interested by the timing between the hyperpolarization and the depolarization of the slow waves. Not the slope itself, but the timing, only the timing. And of course, if you reverse the timing, it is a sort of frequency. It is a frequency related to the transition between the hyperpolarization and depolarization. And the reason why it becomes interesting is because of the graph, the scatter plot that you have on the right-hand side. Horizontally, this is the usual frequency of the slow wave. That is, it is the inverse of the timing between the beginning of the slow wave and the end point of the slow wave. Of course, if you make a reverse, it is the phase of this oscillation, and this phase, if you take the frequency, it's only the frequency related to this entire slow wave that you have in front of you. Now, if you take only the duration between the hyperpolarization and depolarization, you concentrate yourself to what is happening only during this transition between the hyperpolarization and depolarization, irrespectively about what is happening outside of the slow wave. Okay? And indeed, this scatter plot shows you that between the young people, well, it is adults here, not kids, between the with aging, there is no so much difference between the slow waves produced by young adult and elderly adult. However, if you look only at the part of the transition, the slow wave, then there is a difference. And there is a difference in the distribution. And you can see that in the scatter plot, it's not so clear, but when you look at the distribution, there is a difference. So this transition here between the hyperpolarization to the depolarization knows about the aging, but not the frequency itself of the slow waves. So this started a huge story about this transition. And indeed, what we decided to do is to distinguish what was the fast switcher and the slow switcher. The fast transition or the slower transition. And indeed, you can distinguish, you can classify the slow waves with respect to the slow switcher and the fast switcher. Well, it was not so new because at the very beginning, it was probably too fast when noticing it, but in the work of Steriad and others, the very beginning of the slow wave activity, of the slow wave identification, the brain activity, people were speaking about slow waves and delta waves. They were already making the distinction between slow waves below 1 Hertz and slow waves above 1 Hertz, between 0.5 and 1 and between 1 and 4 Hertz. But it was completely ad hoc. It was a separation that was completely arbitrary with 1 Hertz. But in fact, this transition exists, this classification exists, but it is not exactly 1 Hertz. It depends with age, it depends with sex, but there is indeed 2 classes of slow waves. And the data can be, each slow wave indeed can be classified either in the slow switcher or the fast switcher. So if we look at this new parameter of the slow waves, not the slope, but this parameter of the transition, then this is with the kids population, with the kids cohort, you have in the, this is horizontally the frequency of the transition of the slow waves, and the distribution is bimodal. There is clearly 2 classes of slow waves. The slow switcher with the first peak around 1 Hertz, and the fast switcher above 1.5 Hertz. It is clearly bimodal. It is not bimodal with respect to the frequency of the slow waves. It is still monomodal. There is a beautiful shape, but it is bimodal in the transition. So there is 2 classes. If we look at the transition frequency, the transition frequency being the transition frequency between the hyperpolarization and the depolarization, then you can see that this is for the kids during the night. There is a decay, a decrease, but still there is this kind of plateau that may reproduce, but more carefully here, this plateau that we had with the slope. But the slope, it is a mixing between the amplitude and the timing. Here, it is only the timing that makes it a characteristic of the slope. With aging, this property, this transition will reduce. So the frequency, this is the transition frequency. The transition reduce. That means your slow waves makes more timing, needs more timing to make the transition between the hyperpolarization to the depolarization. With aging, you are losing the fast switcher. The slow switcher comes more often, and the fast switcher are probably more difficult to make when you are aging. And probably it is related to flexibility, this flexibility of, I may not have time to make so much comment about the connectivity, but it may be related to the fact that there is less flexibility, the dynamic of the connectivity during the slow wave is aging that for the young people. Okay. During the night, from the beginning to the end, the proportion of the fast switcher decreasing during sleep. So, and this is true also for when you are aging. At the beginning of the night, you produce more fast switcher, and then you decrease with the time, across the sleep. Okay, spindles. So you wanted to see a spindle. So spindle is this fast activity that you can see here, and sometimes spindles are coupled with the slow waves. And this is it will be a particular part of the talk here to speak about this coupling. But if we look about the spindles, or the fuseau in French, now we need a detector. This is more, I would say, conventional. There is not a lot of things to say. It is you have to filter your signal between 10 and 16 hertz. This is a sigma band. Then you need to have this envelope of this oscillatory mode. You take the envelope and then you threshold this envelope to keep 75 percentile. This is the criteria that people are using for all the population, 75 percentile of the amplitude, and then you have the beginning of the spindle and the end of the spindle. And you will see why I'm speaking about the beginning and the end in a second. So this is a sigma activity. There is a criteria about the duration also. The duration should be at least 0.5 seconds and not more than 2 or 3 seconds in your data. Otherwise, it may be an artifact. So the criteria or the parameter, the characteristic of the spindles, well, there is a density, how much spindles you are producing across the night. And again, here for the kids, they produce more and more spindles. There is a maximum at the block 4, so in the middle of the night, and then there's a very little decrease during the night, the rest of the night. What is more interesting, when you look at the amplitude, so the maximum amplitude of this sigma activity of this associated with spindles, there is an increase during the night. And at block 4, again, there is a maximum reach around 15 microvolts, and then it remains. And at the same time, at the same particular time of the block 4, you will have in the frequency of the spindles, it is a sort of plateau, around 12 hertz, and then it increases. The frequency increases suddenly. And remember that you and me, we are making spindles around 13 hertz. So at some point, in some sense, the brain tried to reach a higher frequency that we know that will be produced with adult people. So this is something that maybe related to this morphogenesis of the adult spindle to increase the frequency. And we know that this frequency will be indeed higher than that when you are a young adult. So it is interesting that for the kids, they cannot have higher amplitude together with a higher frequency. First, there is an increase in amplitude, and then they start to increase the frequency. So we speak about now the coupling. And it was, in fact, the purpose of this work was also to investigate how much the spindles are associated to the slow wave activity, because this is, in fact, a biomarker more related with this cognitive process during sleep, in particular the memory consolidation. So here, it is an illustration of the detection, the dual detection of spindle or slow waves. There is a slow wave on the top, and then the spindles on the bottom. And there is a particular point that we wanted to mark carefully was the ignition of the spindle, the starting of the spindle. And we see why in a second, but this was the point that we wanted to mark in the detector. And there is, of course, spindles, and this is a good example here, that are on the top of the slow waves. So a combination of slow wave spindles. You may have spindles outside of slow waves. They may have also a particular importance in the brain activity. And you have also slow waves without spindles. But here, what we want to look at, it was the relation between the phase of the slow waves, which is, again, low frequency activity, and the amplitude of the spindle. And of course, by coupling the phase of slow wave and the amplitude of the spindles that are simultaneous, you have a lot of metrics to assess the coupling between the two oscillations. But in the work that I will present to you, I will not speak too much about this phase amplitude coupling. I will speak about another kind of coupling to consider or to measure this coupling between those two oscillations. In fact, if you collect all the slow waves that are simultaneous to this spindle activity, so the higher frequency, the sigma band, but again, a spindle activity, and then you keep only the phase related to the ignition of the spindle. So you want only to see at what phase the spindle is starting during the slow waves. And then with respect to the timing in the night, block 1, block 2, block 3, block 6, you want to see what is the distribution of this phase of the ignition of the spindle on the slow waves. And then you have a surprise that, in fact, during the night, the kids learn how to produce a spindle in a very particular phase of the slow waves. At the beginning, it is quite uniform. Now it starts, and what we want to look at more carefully is between the phase -5 to 0, 0 it is depolarization, and hyperpolarization is -5. When you look at the oscillation of the slow waves. So the region of interest for us was between the hyperpolarization and depolarization. And what we can see, there is a slope here in the distribution that shows you that indeed, during the night, the coupling tends to optimize the ignition during a particular, around the hyperpolarization. And this, in fact, for the adult brain, it is also what we observe. So this is a kind of maturation of the ignition of the coupling between the spindles and the slow waves during the night in the children, for the children. Of course, we can, and in particular between the block 5 here, and there is this maximum of difference between the distribution of the phase with respect to the other blocks. So this is a point of optimal coupling at the very end of the night for the kids. So of course, probably people say, because in general, the coupling between the spindle and the slow waves is more with respect to the amplitude of the spindle, the maximum amplitude. Where is the maximum amplitude of the spindles with respect to the slow wave? What is the phase of the slow wave where there is a maximum of the spindle? Here, we use more the ignition, the starting of the spindle, where there is this particular moment in the particular phase where the spindle is starting. And in fact, when we look at the maximum of the spindle, where the maximum of the amplitude of the spindle is maximum, there is no difference. All the blocks are all the same. As if the most important thing is to start the spindle somewhere. The maximum will be around the maximum of depolarization of the slow wave phase up. But the most interesting, that you learn, or the system learn how to start the spindle to be efficient. And in fact, it is even more eloquent in the subgroup of kids with high intellectual performance, which is interesting also because suddenly it relates this coupling with something more related to the cognition. So I spoke about the detector, I spoke about the usual characteristic of the slow waves that change across time during the night for the kids. I spoke about the spindles and the characteristic of the spindles that change across night for the kids. I spoke about the coupling between the spindles and the slow waves, and this coupling change across time during the night of the kids. Let's speak about now the spectral analysis. We spoke this morning about spectral analysis. So the Fourier transform. Of course, it is very standard. You look at all. I could have started with that. In fact, I thought it was more interesting to finish with that. Oh, I'm not finished, but so the standard analysis, the spectral analysis. This is a particular. Well, it is not particular because in fact it is a very standard. It is a kind of spectrum that you can find in many circumstances from EEG. This is a CZ electrode. It is an adult. It is not a kid, but it is an adult. It would be the same for any others. perspective. But at the left-hand side, you have a single epoch. So 20 seconds of recording, and this is the FFT, the basic FFT of the signal. Of course, as you know, the FFT is not so much reliable when you have a process and not a function. So there is some trick, there is a tapering technique, there is a Welsh technique that try to bypass the fact that you have a signal with randomness and not really something that where the Fourier transform is reliable, let's say. So in the middle, it is a Welsh technique. So Welsh is subdivide, make some window in which you hope there is enough stationarity to, let's say, be confident that the Fourier transform is reliable. But it's interesting, there is a resampling technique, and we are like it also. So it was in the wavelet domain a long time ago. The resampling technique is a way to delay, contract the signal. And there is a technique interesting that if you change the scale in your signal, you will kill everything in your signal, but what is scale free? Okay, all the scale free activity, if there is a part in the signal that remains the same irrespectively to the scale you are looking at the signal, this part of the signal will remain intact even if you resample the signal. So there is, of course, a corollary of this statement. All the oscillatory or the rhythm of your signal will be destroyed by resampling. You will kill all what is rhythmic, and you will keep what is arrhythmic if there is no rhythm, or if you prefer scale free. Okay. A rhythm, there is a scale. The spindle is 16 Hertz or around 13 Hertz. So there is a temporal scale associated to this particular rhythm. Of course, it is not a pure scale, it is a range of scale, but there is the period of the rhythm. The scale free, the slow waves, there is also a scale, a temporal scale. It is the scale, the duration of the typical scale of the duration of the slow waves. So all those rhythms are related to some particular scale. But in fact, when you are looking at the spectral analysis, most of your spectrum is a scale-free process. It is all these frequencies that are recruited in your spectrum, all this line here. And when it destroyed what is rhythmic by resampling, the red curve, the red spectrum, is what is remaining in your spectrum. And you see that it is all the background. All the frequencies are recruited. And the process, and we don't know how to construct the process indeed, but what is behind this red spectrum here, it is a scale-free activity. There is no characteristic scale, but all the frequencies are recruited with a higher part for the low frequency and less for the high frequency. And Habib should remember a long time ago that it was a starting point about studying turbulence, for example, because this is exactly what kind of spectrum, the sort of spectrum that people in turbulence were looking at. And all the wavelet business was involved in this turbulence analysis because the wavelet was indeed the way to study the scale-free process. No scale in the process. Of course, the wavelet also can be related to what is rhythmic, but in particular, you can consider what is arrhythmic. There is no rhythm because the wavelet are looking at different scale inside your signal. So the spectrum that you can see here, and this is finally the right-hand side, it is a spectrum coming from all the epoch that you collected. And of course, you have a spectrum that show you again in a, maybe I didn't see it, but it is a log-log scale. The spectrum is a log-log scale. This is why you have this line. So you have this background, on the top of which there is some bumps. And the bumps are reflecting some rhythmic activity. And in fact, it is a rhythmic activity around 30 Hertz. This is a spindle activity. You can see that maybe there is some delta, but it's not so obvious. What is obvious, it is a Hydro-Quebec, 60 Hertz, and so on. Okay. So sometimes it's very important to have this the Hydro-Quebec around, because then you can see that when you want to kill what is rhythmic, you will kill, in particular, Hydro-Quebec. You will kill the 60 Hz and all the harmonic coming from the 60 Hz. So what we did was to make this assumption. In fact, this assumption can be validated with the neural mass model. But the spectrum can be written as a constant divided by f to some power. And this is the scale-free part of the problem. Times what we call a residual, but in fact, this residual is much more important than the residual. It is a rhythmic activity. So the rhythmic activity will be inside this exponential of R of f. And the first factor will account in the log scale. Of course, it will account for the line, the straight line that you have in the spectrum. And what we have done during the last couple of months was to make an algorithm that we call R&B, because rhythm and background. But also make a joke with our friend Christophe Grova, who is a player, good musician, but this is another story. And this method allows us now to separate, in fact, to disentangle the power spectrum coming from the arrhythmic part or the scale-free activity and what is part of the rhythmic activity. And this is the rhythmic activity. And of course, to obtain this kind of spectrum that makes much more eloquent the slow wave activity, the delta band, and the spindle activity in the sigma band. Again, it is the Euler spectrum is on the left, on the right side. Of course, to obtain that, you have to disentangle what is scale-free. And in the scale-free part of the spectrum, there is this 1 over f part with an exponent. And in fact, this exponent is not unique during all the recording. And in fact, we can compute the distribution of this exponent, the theta here, the theta of 1 over f theta in the spectrum. And in fact, there is a spectrum. It is not unique. People looking at this kind of strategy in signal processing in general would speak about the multifractal analysis. But this is a model, in fact, the multifractal. We don't need multifractal analysis at all in this kind of business here. But in fact, the fact that there is a dispersion in the exponent of the scale activity can be related to this multifractal analysis of the signals, because multifractal means a monofractal, it is a pure scale-free autosimilar system with unique slope, a unique parameter. But when in your recording, this parameter may change across time, suddenly it becomes a multifractal with this model of this autosimilar system. So this distribution with the black line, it is an empirical distribution of this slope across the time for all the epochs that you collected in the same kind of condition during the non-REM sleep for the adults here. Okay. What is interesting, and this is probably one of the very rare examples where this parameter show two modes. It is multimodal. In general, there is only one mode. There is a spread, and this is what people call that multifractal, but in fact, we don't need this kind of vocabulary. It is only a dispersion of this exponent. It is not unique again. But it is a rare example. We have also an example in the mice, because we also are studying the sleep in the mice, where indeed, at some particular place, location in the brain, there is different mode, or it is multimodal. So there is a complexity of this parameter. It's not a convex set. It is more with different blocks. And in terms of the mathematical description of this kind of process, it is not so obvious, because we don't know how to disentangle now the different mode of this multifractality in the brain, in the signal in general, but in the brain in particular. So we are very pleased about this kind of spectrum, because this spectrum is more related to the rhythmic activity in the signal. Okay? It's try to disentangle the two part of the power spectrum. So coming back to the kids, if we look at the residual of the rhythmic part of the power spectrum, this is what you obtain, block 1, block 2, block 3, block 4, and so on to the block 6. So this is a rhythmic spectrum. And you can see that there is a peak in the sigma band and in the theta band. And across the night, there is an increase in the sigma band. Again, it is the spindle activity that is inside the sigma band, remember that. And there is a plateau, the maximum achieved to the block 4, again and again during the night. And then a slight decrease, but there is a maximum. I remember that it was exactly at this particular time in the night when all the characteristic was trying to evolve the amplitude of the spindles, the slow waves with respect to the transition. There is a lot of parameters that try to optimize at this particular block in the time of the timing in the sleep. And again, this is only the rhythmic part of the spectrum that also evolved with the night. In the meantime, there is also an evolution about this scale-free parameter. And what is interesting is at the beginning, the distribution is more on the right-hand side of 0.5. 0.5, it is a particular frontier where the signal is either persistent or anti-persistent. It is scale-free, but still there is some long-range correlation in your signal. And this is a very long, very old work of people, particularly in Lyon, that were looking at the relationship between the autocorrelation of the signals and this scale-free property. And in fact, you can relate this parameter with the long-range correlation with respect to the persistence of the signal or the anti-persistence, volatility of your signal. And 0.5 is a frontier that separates the long-range persistent activity from the long-range but anti-persistent. So in 0.5, it is like a note, like a white note. So you have persistence and persistent activity at the beginning of the night, and the long-range dependency decrease. You see that the spectrum moves to the left-hand side. So the long-range dependency decrease during the beginning of the night, and then stabilize around 0.5. So again, even with respect to the scale-free activity, there is an evolution during the night in the kids. We don't know exactly why. Probably it is related to the dynamic of the functional connectivity. So this is something that has been done elsewhere in a very different perspective, but we believe also that this scale-free activity may reflect the dynamic of the network involved in the process. So let's make some conclusion, and then I will show you some results coming from, because we wanted to see some source localization, but I will be very brief about that. So there is an evolution of sleep with aging, but also the evolution of sleep across the night, in fact, in the population, in particular for the children. We saw the importance of the canonical EEG graph elements, the slow wave and the spindles. This is not new, but it is again what we try to illustrate in this presentation. And the question is, what about the dynamical connectivity? I did not show you anything about the connectivity itself. Does it change? It changes across the night. This is some results that have been obtained in fMRI in particular, but I will not speak about that. Also, the maturation of the coupling across the sleep and the sleep disorders. So this is another aspect that we are looking now. All what I showed you was with healthy kids. There is no sleep disorders. There is some cognitive distinction between in the cord with respect to, as I told you, the high performance, intellectual performance in the SCID. I would completely ignore this parameter, but in fact, we have other cords with narcolepsy and apnea. And indeed, there is an impact. We see how much all what I show you about the inventory of the slow wave and the spindle and the coupling is impacted during the night in the kids with respect to the disorders. I'm much more involved now with this rhythmic activity and the arrhythmic activity, and that we can disentangle at some point in the signal. And in fact, and I will let you with this discussion, probably we should revisit a lot of things with respect to this separation. In particular, we should maybe look at the coupling of the oscillatory pattern, but trying to disentangle, to isolate what is purely rhythmic. Because up to now, when we are making all those coupling between oscillatory in some frequency and other oscillatory on other frequency, we take all the spectrum, all the part of the signal, and in this coupling, there is also the scale-free part that is taken into account. And it is probably biased by the scale-free part of the signal, because we know that when you are computing the FFT, the Fourier transform, the Fourier analysis, up to now, we don't know how to separate what is belonging to the scale-free activity and what is belonging to the pure rhythmic activity. And even with that, we make some coupling. So, question, maybe this coupling is much more dominated by the scale-free activity than from the rhythmic activity. More than that, if we see that this coupling is changing, does it change because of the scale-free activity is changing across aging, for example, or because it is a pure change with respect to the rhythmic activity? Because we know that the arrhythmic slope, this beta that I show you, change with aging. So maybe it is only a matter of change with respect to this parameter, and the rhythmic activity is still correct or still stable across aging. So I think there is something that is very important to do now, but it is not so easy. We know how to disentangle the power spectrum, but we don't know how to disentangle the time series. Okay? Because to make the coupling between the oscillatory pattern, we need the time series, of course. We cannot stay in the Fourier domain, in particular in the power spectrum domain, because this is the phase are completely lost in particular. So this is another problem. I think it will be very, I will be quite, we can bet today that the thing will be probably changed if we success to disentangle what is belonging to the scale-free activity to what is belonging to the rhythmic activity. We know, for example, that when we are looking at the arrhythmicity of the brain activity in epilepsy, this is an old work that we have done with Jean Gottman, a student of mine, you can predict, well, you cannot predict, but you can improve the prediction of a seizure, for example. So this arrhythmicity knows something about the activity, local activity in the brain, and it was not locally in the brain where the seizure was occurring, it was remotely. So indeed, it was a part of the brain that was changing with respect to the arrhythmicity, but it was not involved in the seizure itself. So probably, this is again an hypothesis, the arrhythmicity is more related to the network. The fact that there is some hub, for example, involved in the connectivity pattern. And for some reason, this particular part of the brain, this particular hub, show and know something about the arrhythmicity that reflect the fact that it participates to a network, and this network will be involved indeed with the seizure later. So there is a lot of route now, open road, with respect to this problem that it is a very hot problem to separate the rhythmic activity to the arrhythmic activity, but again, we need some more study to make that at the level of the signal. So let me give only some flavor that what we are doing now. And then for the time, well, I started a little later. Yeah, 5 minutes. Yeah. Good. In progress, what we have is the dynamics of the interactions. This is a work that has been started a couple of years here with people from Marseille, Christine Roubaud and Bruno Torresani. There is still some work to do to improve the things. It is source localization. It is exactly what Adi wanted me to speak about today, but you have to invite me for this kind of discussion. The source localization from EEG and MEG. We revisit this the formalism in order to not to localize or to make this algorithm working at each time step. Well, we improve it by looking at the activity at each time frequency step, by making the same algorithm but at the level of the time frequency analysis. So it's very easy. You take your signals that you measure, instead of looking at each temporal sample of your signal, you project everything in the time frequency domain. That's very difficult. And then you localize all the coefficients of this time frequency domain in the brain. So you make you will infer the time frequency activity in the brain. Okay? Why? Because two reasons. Very trivial reason, the wavelet will compress the data. It has been designed for that. There is less wavelet coefficient that you have sampled in time. There is this kind of compression that has been indeed emphasized a lot at the very beginning of the wavelet technique. The wavelet representation generally compress the data. So instead of localizing each time step, it is much more efficient to localize the time frequency, the wavelet coefficient, and then you can reconstruct your signal from the wavelet coefficient that you have, for which we have made the inference. This is the first point. The second thing is, if you know that there is some particular scale and time where you want to investigate something, the time frequency allows you to target a particular box in the time frequency domain to see what is happening at a particular time at this particular scale. So again, the scaling property is coming back with this wavelet technique. Now, what we have done here with this work was try to put all together the covariance, the spatial covariance as we know across the electrode, but also the covariance in the time. So it is a dual covariance, time and space, in one shot, in a unique inference, in order to take into account the temporal covariance between the signals. And the reason why we wanted to do that, and this is again something that is not finished, is to make some inference about the networks themselves and not the regions of the activity of the brain. What had been done also, this is a work that has been published recently, but in fact the work started a long time ago, was to use exactly this kind of inference, so the source localization, but to localize the propagation of the information along the fibers. Of course, if you give me some data coming from MEG or EEG only, probably I will have some difficulties to show you the propagation of the information from the occipital to the frontal for some reason. But if you give me also the fibers, the white matter and the fibers, then I can put that in my model to see if I can make the inference about the propagation of information. And this is exactly what I've been done with people in Nice, in fact, in the source of the France. And this is a very beautiful, beautiful algorithm that makes the propagation of the information for some particular task. What I can show you, and this is a result, I'll come back to this slow wave activity. I show you that there is a fast switcher and slow switcher. There is a classification, a data-driven classification. It is not coming from an ad hoc frontier in the frequency, with the frequency of the slow waves. We are using, again, the transition between the hyperpolarization and the depolarization of the slow waves. We can distinguish the slow waves with respect to this transition between the slow and the fast switcher. And what can I show you here is during the transition between the hyperpolarization and the depolarization, what is the connectivity involved on the scalp? So there is a couple of metrics that we can use. Coherence. Coherence is not so nice because there is a leakage. So imaginary coherence or the WPLI. There is a lot of metrics that can help you to make this connectivity across the EEG derivations. And what we want to see, it was how much the network changed across the time, along the time, at the scale of the slow waves itself. So this is what we can see here. There is this connectivity change, and the connectivity change in particular just after the hyperpolarization of the slow waves. And then this is for the new people, for the slow switchers, so the slow waves that are low frequency from the transition, and then decrease at the beginning. This is for the fast switcher. The connectivity is less involved. Again, the transition is more fast, it's faster. So clearly, the connectivity is helped through the transition with a longer duration than the transition with shorter duration. This is for the young, and this is for the older people. So clearly, for the older people, there is aging impact. The fact that there is a dynamic that can stay during the slow waves, and for the fast switcher, it is completely abolished. So this is for the slow waves where there is no spindle on the top. If there is a spindle on the top, this is another part of the slow wave, then the connectivity decreases. It decreases for the young, but still exists for the young people, for the slow waves, slow switcher, sorry, mainly abolished for the fast switcher, and then it is the slow waves that are more fast in the transition. And for me and Admid, there is nothing in the connectivity. And this is interesting because probably it means that there is a competition between the network involved during the slow waves and the network involved with the spindles. And we knew that there is some network that dynamically change with the spindle. This is the very last part of the work that I want to show. This is the older work, in fact, done with Meg. So what we have done, we collected sleep in the Meg facility, so that's the University of Montreal. And what we want to show was to see, well, we investigated a couple of things, but in particular the slow waves again. And what we have here, it is the time frequency of the slow waves. So we have the frequency and the time. And what we distinguished was the beginning of the slow waves at the frequency that is a bit higher than the end of the slow waves. In fact, what we, sorry, I'm speaking about slow wave, but in fact it is spindles. So again, I have to rephrase everything. The frequency was a bit high for slow waves. So it is spindle. So here we were concentrating on spindle activity, again, around something like 12 Hertz, so in this range of the frequency. And what we show is at the frontier of 12 Hertz, again 12 Hertz, we had this part of the beginning of the spindle with higher frequency and the very end of the spindle lower frequency. In the spindle community, there is the idea that there is two kinds of spindles, the fast spindle and the slow spindle. Personally, I think that there is a unique spindle, but there is a fast activity at the beginning and there is a phase off at the end of the spindle. Okay. So, and this was a kind of example here where we show that we had this illustration that a spindle itself is a combination between a fast activity at the beginning and a slowing down at the end. So we make the localization. I will not speak about that, but what was interesting was the fact that at the beginning of the spindles, you have this kind of connectivity pattern. It is in the source space, so I will not show you how we proceed to make this inference. It is this maximum entropy technique. In the weighted domain, there is a lot of things that we incorporate in this technique of source localization. And once we localize the spindle activity, in particular, we are looking at the spindle activity at the beginning of the spindle and the spindle activity at the very last part of the spindle, two pieces of the spindle, for all the spindles collected across the night. And then we make this assessment of the connectivity on the source space, frontal part, parietal part, medial part, temporal and occipital. And then by this metric, it was at this time the WPLI, the weighted phase lag index, which is a common metric in the source space. I tried to be careful about the leakage. We had this graph of connectivity at the very beginning, and then at the very last part of the spindle, we have a more dense connectivity pattern. At the beginning, we have only in the frontal part the connectivity between the two hemispheres, and at the end of the spindle, we have this massive connectivity that makes the interconnection between the two hemispheres. So we knew already that there is a connectivity, a dynamic of the connectivity during the spindle. So what we want to know is how much this competition between the slow wave connectivity, and again, as I show you, the connectivity of the slow waves up to now we have this measurement on the scalp, of course, we should localize, and we did that, in fact, a couple of years ago, to make the localization of the activity related to the slow waves and to see how much the connectivity related to the slow waves and the connectivity related to the spindles, how much they collaborate together, and maybe there is a conflict or maybe there is an interaction so that the two cannot be occur. And this is exactly what we try to illustrate or to find in this work here on the scalp with the EEG more recent. That's it. Thank you.
So thank you very much, Jean-Marc. It's a nice presentation, even if it was not on the reconstruction process and MEM, but it was really, really interesting, mostly for signal processing and sleep in particular. So I think that the floor is open for a question. Maybe to let you thinking about the question, I can start with one. Then I have to. Oh, okay, go ahead.
If you don't mind.
No,
So I know I'm not too well versed with a lot of the literature that relates to EEG. So maybe my question will sound very naive, but
they are the most difficult.
when you were first talking about the slow waves, we were talking about the thresholds and the changes that occur with sex and age. So for me, what I was thinking in my mind are these sort of proxies for something more implicit, which is the actual morphology of the brain. Because when we're talking about these differences that occur, we're also trying to take into account, let's say, the brain structure, how it changes across time. And when we're talking, I guess, the first thing that came to my mind when we're talking about transition differences between old and young, maybe it could do with the fact that as we grow older, the complexity of the brain increases. And let's say if we're thinking about like this sort of, I don't know, like let's say a transmission line, like when you're young, maybe it's going to be very small. When you're old, it sort of becomes larger. And maybe the question isn't, is the transition due to the brain trying to adapt in a particular way to account for this more complex network or this more complex brain structure? And these differences in thresholds have to do with the brain having to cope and disperse its energy in a particular way because it doesn't have infinite energy. So